Now, one of the key applications of integration is, of course, finding the area underneath curves. So my first bit of advice is to sketch what it is that you've got to find. Remember also that when you're finding integrals that are below the x-axis, you should do those separately because they're going to come out as negative numbers, and yet the area itself needs to be positive. So you should find your integrals and then carefully add your areas at the end. So I've got an example here. Find the area enclosed by y equals cos half x, or x on 2, and the x-axis between 0 and 4 pi. So the first thing I want to do is sketch this. And to sketch it, I need to consider what this curve looks like. I know what y equals cos x looks like. It starts here and it goes down and then up again. And it has a period of 2 pi. But remember that the period of the sine and the cos curves is not just 2 pi, it's 2 pi on n, where n is that number that's there. So if I do 2 pi divided by half, dividing by half is the same as multiplying by 2, the period of this one is going to be 4 pi. That means it's going to start up here at 1, and when it goes down and then back up again, it's going to finish at 4 pi because that will be one full revolution. Now, my sketch is not perfect. It doesn't have to be amazingly to scale. It's just showing you where everything is so that you can get things right. So if that's 4 pi, the halfway mark is 2 pi, and that tells me that these special points here and here are pi and 3 pi. So I'm finding these areas here. Okay, and straight away, just by shading them in, I know that I'm integrating and I'm finding areas and I feel like I know what I'm doing. Now, we need to find the areas separately. There's two ways you could go here. One way would be to label the parts. So you might want to say that this is area A, this whole bit could be area B, and this could be area C. Divide it into 3 bits. Find them separately. There's going to be a whole lot of work into that. And that's an ideal way, especially if you've got a curve that doesn't have nice symmetry and it's just got random sized sections above and below the x-axis. With this one, I'm tempted to actually use what I know about the symmetry here. Now if I just undo my shading a little bit, can you see that the size of this shaded section is actually the same as this section down here? And that's the same size as this bit and this bit. So I know that if I find the size of this part and multiply by 4, I'm going to have the whole lot. Now, when you're applying this sort of strategy, you need to be really careful that an examiner can actually see what your reasoning is and why you've multiplied by 4. So what I would do is probably just label this part A, maybe without shading it, B, C, and D. Perhaps it would have been neat to just write it in there. And then when I go to find each section, I can literally just investigate. So to look at the area A, I know it's going to be positive because it's above the x-axis. So it's between 0 and pi. I'm going to need to integrate my function. And I need to consider, is this a perfect question? Well, a perfect question would have a half out the front, wouldn't it? So you've got two strategies. You can either think this through in your head and make up that fix that you need in your head, or you can rewrite your question and say, I wish I had half out the front, because now I've got a recipe for that on my reference sheet. But you can't go changing your question by putting multiplied by a half. You'll need to multiply by 2 as well to make up for it. Now I've got a recipe I can follow from my reference sheet, and I've got that 2 that needs to stay out the front. So now I can use my square brackets to integrate this section. I know sine differentiates to cos, so cos integrates back to sine, and I need to just put down, whoops, not cos, the sine of a half x, and I've got my bounds here. Now I can sub in, I've got the sine of pi on 2 minus the sine of 0, and the sine of pi on 2 is 1, so I've got 1 minus 0, which is just 1, and this gives me 2 square units. Then I would reason and say areas A, B, C, and D are equal in size. How do I know this? Because of the symmetry of the curve. So literally just state that in a sentence. Because of the symmetry of the curve. And that might seem time-consuming writing that sentence out, but I think that's quicker than doing all this working again for the second section, and then all over again for the third section. Okay, if these weren't the same size, you'd have to do all of that working, but if you can come up with a shortcut that saves you time, do so and explain what your thinking was. That is your working, because it's your reasoning. So now I've got, therefore, the total area equals, and I've multiplied this by 4, and I get 8 square units.